All right. Hello, everybody. Welcome to the CDR for the Vision Project for Group 14. That's the Visually Impaired Spatially Interactive Orientation Network, or more or less a long set of words to get a cool acronym. Very excited to share this project with you. We're actually working in conjunction with Group 19, the Scratch team as well. We're going to get right into things here. So an introduction, what is Vision? Basically, we're trying to bring our love of billiards to the visually impaired, give the less fortunate an ability to play a game. It's been around for centuries and that our teams both love and enjoy to play. What we're really doing within this project is we're developing several proof of concepts to develop different assistive measures, again, to bring this joy of the game to the less fortunate among us. We're inspired to try to do this and hopefully inspire future development of this assistive technology, either in billiards or in other systems to try to, again, bring more ability to those that maybe do not have it. We're trying really to make the very difficult and the impossible seem feasible. Once again, I want to reiterate, we're actually working within two senior design teams here. So the Vision team is actually the more or less could be thought of as the table team here. Most of the subsystems that we're working with are going to be located on the table. There is our localization system that is located on the user. And the other side, which is the Scratch team, is going to be the primary user side of all of our subsystems. One of the main goals that we've also had within this project is to limit this dependence between the two teams. We're only really sending small amounts of data across the two teams in order to have that independence and make sure that if one team passes and the other possibly does not, that that one team will not be penalized for the limitations of the other. So to go in further to what our team is developing, we're going to go into the core subsystems of our project. So first of all, we have computer vision. That's going to be getting the active state of the billiards table with use of cameras. We're going to be having an AI developing some shot selection for us to give the user the proper best shot that's on the table. Then we have our user localization system, which we referred to before. That's going to be actually actively on the user. And then finally, our user guidance system that will be utilizing audio guidance to move our user around the table to desired positions. The group members, so our distinguished gentlemen, yes, very distinguished, yes. So we have Noah Harney here, computer engineering, Aaron Crawford, also computer engineer, Arsen on here, electrical engineer, and then myself, Alexander Parody, another electrical engineer, and then honorary member, little Byron the koala here. So great to be working with these fellows and be working on this project and introduce them all to you.
As previously mentioned, a lot of what we're doing is broken down into 4 different systems. Having 4 different members, it kind of made sense for us to divide it more or less equally into different goals and objectives. So our system overall should have different tools and facilities that will assist the visually impaired individual to play the pool game from beginning to end. A lot of it will be, as mentioned earlier, localization of the user in real time, capturing the state of the table, basically the different ball ceiling play and the location of the different BL holes in real time as well. The system has another system that we have in this design is a system to determine what is the perfect and ideal shot, more importantly, feasible for anyone depending on the skill level, based on the current state of the pool table and as well as the current location of the user. And based on that ideal location, we need to have another system to move the user from his previous location to whatever the perfect location computed by a previous system will be in order for him or her to make that perfect and feasible shot. We're going to go over some of the requirements. At a basic level, a lot of this is based either on accuracy or latency. For instance, for a localization system for the pool table itself, we need to be able to locate all billiard balls within our given coordinate system that all our individual systems will agree on within 15 pixels of accuracy. We also need to have a latency that algorithm should work within 5 seconds. So if any change has to happen on the pool table, that needs to be computed more or less in real time. Under the same vein, we should be able to locate the user within 10 seconds at the longest, broken down to about even 5 seconds at worst. And as well as locating him or her fast enough, we need to locate them accurately enough. And currently, the 1 foot of accuracy is estimated based on the fact that the human torso will still take about half of, even twice, if not more of that unit of length. So we'll still be able to determine where the user is, no matter where around that foot of error they will be. On the next slide, we have some more of those accuracy constraints. Another one, for instance, is the shot selection from the previous slide as well. should be made within a minimum of 5-degree increments specificity. And then on this slide as well, we have some more miscellaneous specifications. For instance, a financing specification. A lot of these projects being self-funded. We're trying to get that the total cost of not only the pool table, for instance, but also all the individual aids that we'll have should not exceed $800. And then we're able to position the user, like I mentioned, within 1 foot of accuracy, and orient them as well within 15 degrees in either clockwise and clockwise direction from where they're supposed to make the perfect shot. You can read the rest of the requirements. I kind of go over some different constraints, but we're going to be moving on to the next slide.
This slide is the overall system diagram. From it, you can see our processor selection, which will be based on the Jetson Nano to power the shot selection algorithm and computer vision. We will also be using the ESP32 for the user localization system and the user guidance system. You can see all of the inputs and outputs between the various systems, as well as the peripherals for each. This is a summary of the subsystems. For the computer vision system, which Noah has made, we will want to determine the location of all the billiard balls and send them to the shot selection algorithm. We will also be watching for the outcome of a shot in order to send to Alex's user feedback system. The shot selection algorithm will take input from the computer vision system and calculate the best possible shot. This system is responsible for sending relative angle and force to the scratch system, which is the other team. We will also be sending the perimeter location along the pool table to the guidance system. User guidance is Alex's system. It will receive perimeter location from the shot selection algorithm, and it will then communicate with the localization system back and forth to determine the difference between current and desired position. It uses a speaker array to communicate with the user where along the table it should be moving towards. The final system is the user localization system by Arson. It determines the real-time position along the perimeter of the table and is able to send that information to the guidance system.
So as mentioned before, the computer vision system is responsible essentially for everything related to the pool balls and their location on the table. We will be using a camera and computer vision algorithms to be able to detect where the pool balls are on the table and then localize them to a predetermined spot on the table. To make this a little bit simpler, instead of having solids and stripes, we're going to be using blue and green balls. They essentially mimic the same thing. One player will be blue balls, one player will be green balls. Black and white balls still have their same respective meaning. And overall, the computer vision is going to be responsible for determining the outcome of a shot as well. And this is essentially done by comparing the start state and the stop state of the table after a player has taken a shot. So this is more or less what the camera is seeing. So here we have our pool table, and what you can see is that we have these different colored balls, and around the balls is essentially a white circle. The white circle there is what the algorithm has seen and identified as the pool balls. One of the optimizations we're trying to look into is trying to get a tighter bound on these circles, but overall, I think that this is pretty good for our system so far. In terms of doing computer vision, as well as the next system, which is the artificial intelligence system, we do need quite a strong processor. So we ended up looking at a few options. We looked at the Coral Dev Board, the Jetson Nano Development Kit, and the Raspberry Pi. And as anyone that is looking at these type of boards knows, they're pretty hard to get. The prices here are actually representing the MSRP of these, and most of these boards you cannot get. So one of the main deciding factors was actually the ability to get a board. What you're seeing here on the right is a Jetson Nano from a third-party company called Seed Studio. It was not $99, it ended up being $200. And for most intents and purposes, it has been good. One thing that we did not foresee prior to purchasing this was that the GPIO, which is the 40-pin header on the right side, if you can make that out, the configuration driver from NVIDIA does not work because this is a third-party board, and there currently is no solution to getting that driver to work between NVIDIA and Seed Studio. So that has altered some design decisions as the project has progressed. Looking at the actual camera for the computer vision system, this table on the left shows some options here. The primary things that we were considering was the price of the camera as well as the field of view. A variable field of view is important and a large field of view is important because a larger field of view essentially means that the camera does not have to be as high above the table. The other design decision was, do we have a ceiling mounted or fixture mounted camera? In terms of this being proof of concept, we ended up going with the fixture mounted simply because of the mobility of it. If we were to mount this and this be a functioning design in, say, a pool hall, we would probably opt for a ceiling mounted because it will provide better resolution and it will also be more reliable. But simply for the fact of mobility, we have designed this fixture on the right. And if you look at the very top, there is a camera attached to the end of it. So overall, the computer vision system does two things. In the first startup of a shot, it takes a picture of the table and determines how many balls are there, what type of balls, and their location. At the end of a shot, the same computation is performed, except that now it compares the end state with the start state, and it looks at how many balls are present to determine if a ball was made. The actual algorithm to do this was primarily hue circle transform using some image manipulation and filtering. We considered quite a few computer vision platforms and ended up going with OpenCV because it's lightweight, it's simple, and it's supported in Python. So some of the issues that came up were trying to deal with camera glare, porting different colors of pixels on the balls. Current solution is to actually sample 121 points around the ball rather than just one. And we can filter out some outliers, and this makes the algorithm quite a bit more robust. I've kind of touched on some of the game state in determining the outcome of a player shot, but overall the system has been able to successfully locate and determine the color of balls reliably. We've done over 150 ball tests and we've had one error. And I think that is an acceptable accuracy rating. And it's been able to successfully determine the outcome of a shot given two game states, which basically determines if a player made a shot or not.
For the shot selection AI, the design and components of it, the goal of the algorithm is to determine a realistic shot and output the angle and force to achieve this shot. The input would be from the computer vision system and is a current table state, which shows the X and Y location of the balls along with the classification of the balls. The output will go to first the scratch team and giving it the force and relative angle to hit the cue ball. This is done communicating via Bluetooth from our Jetson Nano to the scratch team's Raspberry Pi. The second output will be to Alex's guidance system. This will give him the perimeter location and wall number. Here's a class diagram of the shot selection algorithm. It has both my components and the components of the existing AI and simulation open source software we used. As you can see, it's got the realistic AI, which is ours, as long as the shotfication system. And we also were required to integrate within the Pool Genius software, which we will talk about later. The requirements of the shot selection algorithm are that it produces an output in under 20 seconds. It produces shots in which the end of a 3 to 4 foot pool cue will not intersect with the dimensions of the table. This basically means the shot is reachable. And it ensures that a 7.5 degree sweep in each direction from the shot angle will be clear of any obstructions or balls. Another thing we would like to point out is due to mutation limits, we will only be considering the angle on a top-down view of the pool table. It is assumed the user will strike the billiard ball directly in its center. We chose to do a heuristic-based AI as opposed to machine learning. The heuristic-based gives us rules which follow the common rules when selecting a shot that a real person would choose, as opposed to machine learning algorithm, which may produce results which a regular person would find to be a strange choice. We decided to use an open source project called Pool Genius. This was a good base for our AI, and it used a heuristic-based model. It simulates thousands of shots from different angles and forces, and then assigns each one a score, the highest score being selected as our best shot. There were some issues with Pool Genius. There's no documentation, development, community, or unit test for this. There's also an unneeded front-end system, which we had to take apart for our final product, and we had to learn how to simulate a single shot as opposed to running through an entire game with their system. The final issue was that it lacked the ability to suggest realistic shots and focused on winning in as few moves as possible. Here is a visual representation of our shot selection algorithm. As you can see, the sweep is free for the cue stick, and it gives the wall number, position, and relative angle. In order to come up with more realistic shots, we implemented what we call a complexity AI. It tracks things such as total collisions, distance of the cue ball before first contact, collisions with the wall by the cue ball, total collisions per pocketed ball, and the total distance traveled per ball. This is the complexity formula we came up with. A higher score would mean negative points, so we would want to reduce complexity as much as possible. In addition to adding these scores together, we also have an additional weight which will be multiplied by each of these. This is done in order to balance the equation to our needs. Additional points on the heuristic-based system are that a billiard ball made will give points. There's a diminishing return based on a square root function. So making more balls will not be a linear gain in points. Making an opponent's billiard ball will also give negative points. And there's an easy shot modifier, which will give more points for shots that hit in the center of another billiard ball. A scratch will give negative points. The shot verification system is a way to ensure that shots are not obstructed. An obstruction can be a billiard ball, the user not being able to reach a shot with the pool cue, or the user's handedness making a shot more difficult. By limiting these shots, we save computation time for simulating. Some of the formulas under the shot verification system are to calculate the relative shot angle. As you can see, the left side gets negative degrees, and the right side gets positive degrees, with the center being 0. Another thing is that we ensure a clear path of the pool stick. We use a raycast algorithm against circles to ensure that no balls are within a 7.5 degree sweep in each direction. We also determine shot reachability based on the player's position along the pool table, the length of the cue stick, and the player's handedness. In this case, we assume for right-handed players. The final function will be to determine position. This will be sent to the user guidance system. It calculates position along the perimeter of the table using a raycast algorithm, and also finds the wall number.
I'm gonna go into the user localization or components for this subsystem. Just to reiterate, the reason why we need this localization subsystem is to make sure that at every single time during the game, we're able to localize where the user is for either to confirm that he's made it to the right location for the shot, and just to confirm and give him more feedback along the road. So this location system should work with barely any latency to confirm that everything is working in real time. It should be able to be mountable on the pool table for ease of deployment. It should abide to our cost requirements. So basically the system should not be incredibly expensive, no matter how much accurate paying a higher price will be. It should be able to localize only the user of the vision system and no other pool table player on the table, and it should be able to communicate with every other subsystem involved. So just a few things that we thought about when researching for different sensors and technology that can be useful. Just to gloss over a lot of these and combining a few within one umbrella. We thought about ultrasonic sensors and iris sensors, but a lot of what they're used for is for obstacle detection, because in contrary to one of the points I mentioned earlier, they will not be able to determine or locate specific users. There's also different disadvantages. For instance, ultrasonic sensors have been very sensitive to surface absorbing devices, such as glass, or just iris sensors being very subjective or sensitive to body heat. The system will also need to have a lot of these sensors to be able to cover the whole realm of the pool table, which once again will end up being possibly way too expensive and involve way too much wiring, or at least having a system that will be way too convoluted for the goal of this particular project. Another subsystem that we thought about was RFID. Basically, we could have used RFID tags to locate the user around the pool table, but RFID readers are way too expensive. It ended up being not very cost effective. One of the systems that we almost ended up going with was Bluetooth low energy beacons. The main issue for this one, at least the goal for this one, will have been, first of all, having an ESP32 communicate with those beacons and read those RSSI values to be able to compute the user's location. Having tried that and tested it out, the main issue here is that the accuracy was straight up terrible, especially if we need to locate the user within a more or less 7 by 3.5 feet region. It definitely does not work out for this experiment, though it will be great for different applications, just not for this one. Other issues here will be multipath fading, where the signal reading will bounce around different obstacles, including different players. Last but not least, radar and lidar will be great additions with how much accurate they can be using current technology, but will be once again way too expensive. Okay, so now this is the winner based on the pool of options that we had, which is ultra wide beacons from STMOD, which is the company that manufactures these beacons. They're extremely cost effective for this application, being about less than $100 for this total cost. This specific product comes with 3 of those beacons. That will explain why we'll need exactly 3 of these beacons in the next slide. But we're able to use these to measure accurately distances within centimeters, or even which falls within one of the requirement specifications to locate the user at the foot of accuracy. Beyond this, the technology used for this is the same one used for in AirTags, which is just the ultra-wide, the UWB chip embedded within the system. It also contains different inertia sensors to make sure that we're able to not only adjust for those signals, but also adjust for different motion within different objects that have been localized by the beacons. Other cool features of this is there's an included battery. If you go back to one of the specifications, is that this system should be able to work for about a year, no matter how much it's been used. These beacons are constantly on at every single time, so we're able to use this for about a year, and it just needs to be replaced as needed. Other advantages is that the company itself provided us with an SDK for programming purposes, which we'll get into it in a minute, and we're able to use this for a system, for a localization system that I'm going to explain using the next slide. So on this slide, we more or less describe how we're designing this localization system. We're designing the system itself will be an app on the user's phone to once again allow every user having, the only requirement here is that the system only works on iPhone models 13 and plus, basically because, like I mentioned earlier, this is more or less a technology that Apple has a lot of input on, so most phones will not be able to use this, but at least most modern phones and anything above that will be able to communicate with these beacons, and the user will be able to the user's phone will be the main thing that these beacons are going to locate. The beacons itself, once you're using the SDK from the company, which was one of the hardest things to use, one of the hardest things within the project, associating the beacons, these sensors and the beacons code with the current code for the project. The whole app was designed using Swift, and the app design was made to be aesthetically pleasing for visually impaired individuals. So different features like usually obnoxious buttons to make sure the user can only press on 2 different options. The buttons also include sound feedback to make sure that the user is pressing the right thing, and different vibrations. So even if you just press on it blindly, you know exactly where you've been pressed. The user doesn't have to worry about the app at all. Just turn it on his phone and everything else will be communicating in real time. So on this slide, you now have what happens after the user's distance has been received accurately. So from this point on, once the distance has been received from the app, the communication with different subsystems is done through MQTT, or message query transfer telemetry, which is basically realized on an online server in such a way that the distances are being communicated directly from the phone to that online server, and then from the different subsystem can pull those distances. For instance, one of the subsystems that I'm going to be using, that I'm going to make use of those distances for, is one to compute trilateration. Once, like earlier mentioned, we have 3 beacons. The current goal is that the beacons are going to be positioned on the table at strategic points, and then based on the distance received from each beacon to the user's phone, we're able to design spheres or circles of interval. And like you can see in the diagram, the intersection of those spheres or circles will give you the user's position at every single time. So this system will basically go from the user's phone to that online server. Online server will be pulled down from a JSON through a Python code, and the Python code will compute either 2D or 3D trilateration in real time to determine X and Y positions of the user at every single time based on the latency that we give in within the system.
All right, thank you very much, Arsen. And we're going to be building off a lot of those concepts on the user localization. Rating these slides here for user guidance. These 2 systems are probably the most interdependent upon one another, and we'll go into a little bit greater detail on that on the software mapping and feedback loop section. The main and core concepts we're going to cover in the user guidance system here is going to be, the general overview of the audio guidance for the user, what that kind of entails, how it's going to look and whatnot, goals, and the handoff then to the Scratch team, the speaker array that we'll be utilizing, the audio output itself that we have decided to go ahead with, and some alternatives that can also be implemented. Once again, the software mapping and feedback. And then finally, this is where we get to our PCB, so the system integration for this portion of the project via a printed circuit board. Okay, very cool. So we're going to go into a few different concepts here for the speaker array. So first of all, for our guidance goals, X marks the spot here. Again, based on the AI slot selection that Aaron discussed previously, we are trying to get the user from wherever the user localization point comes from to that final destination that we are looking to orient them towards the pool table. In this case, and we actually do have two different options for how we can interact with the user once we arrive at the table. Our core goal for this project is going to include the user sitting perpendicular to the table, so that is facing in the direction of that table, facing in this case, the green velvet, which is shown on the screen here. The purpose of this is the Scratch team basically has that being their primary initial origin point and orientation system they have for calibrating the user. Setting up for the Scratch team, make it an ideal handoff. The other part of this subsystem that we have is we have a 12 speaker system. So this actually kind of brings into the secondary portion of what we can use for our when we get to the destination for the user. Actually, for guidance, we're going to primarily be using these corner speakers that you see on the table there, because that's really all you need, since it's basically a binary decision on which direction the user will be going. So in reality, you only need the corners there in order to actually guide that user. But the additional speakers are there for the stretch goal that you see on the bottom here, talking about angular position. So that would be if the user gets to a point, then we then want to further guide them in an orientation around the table. Again, this is more of a stretch goal. It's actually not integral to the two sub-teams here and the overall process of making the user make a shot. But we do want to test out, again, multiple different ways that we can assist the users. That's going to be helpful for getting the user oriented in a separate way from what the user team is using. So the audio method that we're using is going to be square wave pulses. You can see that in the bottom right of this slide here. Basic 50% duty cycle PWM waves here. We found that that was very useful in comparison to analog waves, as when an analog wave comes on, it's a little bit harder to determine that origin point after the initial starting of the speaker. So we found that a pulse was a bit better. We are going to continue to develop through this and also check out if we need audio amplifiers for our speakers. We currently do not have that in the design, but we found that currently the 2-watt speakers are pretty good. We're going to continue to see if that is good enough for development purposes. And again, we've talked about the corner outputs and the directional options. That part is pretty straightforward. And as you can see up on the right side of the screen, that is a picture of the speakers that we're actually utilizing. Those will be wired under the table to the PCB. Yes, so this is just a basic prototype that we have already made. We currently have the PCB in development, which we will go into further detail very soon here. But this is just a basic picture of what we had, and that gave us a pretty solid PWM output on this speaker here. Again, this is a 2-watt speaker that you see here, ESP32 that you see on the bottom of the picture there, and then a demultiplexer. In this case, we're using it to select outputs. So we basically have a signal that enters in there and then is selected based on some binary outputs from the ESP. And then that picks which speaker output. So we've done some pretty solid testing there. The hardware looks pretty good. Okay, so on to the guidance software here. So we're going to be, one of the core parts of this is communicating between the ESP and the Jetson Nano. This is very important for our feedback loop. We're going to be integrating with, again, the user positioning system. So that's going to be basically figuring out, based on the position, how much more guidance we need until we actually get that arrival signal basically getting fed back into the Jetson Nano. We'll be utilizing SPI or Bluetooth there. Want to kind of have both options available to us. The ESP actually has a built-in antenna for Bluetooth purposes, and we put in SPI jacks, which we'll cover in a moment. The localization array we're going to be using is going to be having this array that you see here on the right side. Really, it only needs to have this one-dimensional depth, as we want the user to be as close to the table as possible, and depth is not actually really going to be too important to us. More of the position will be what is key, and it is only really a binary decision for the speakers. So based on where the user is and where the destination is, only 2 options should even be available, and then only one of those will be selected based on whatever the shortest distance is. PCB design. So we talked a little bit about this, how this system is going to be integrating our printed circuit board. So some integrated components. We have a microcontroller, our speaker connections and control, power regulation, push buttons, USB connection, and the Jetson Nano communication for SPI. We're going to go through each of those pretty briefly here to show the schematics, and then the final model breakdown in 3D. So to start things off, kind of the central portion of control here, you see the microcontroller, the ESP32 here. It has its basic kind of connections for power regulation and safety concerns that you see on the left side, and then plenty of jumpers that go to the various subsystems on here. In addition, you see the voltage regulator that we're using from Texas Instruments. as well as the SPI header. That would be what would be used to physically connect to the Jetson Nano. And once again, we are kind of opting between the SPI and Bluetooth purposes. If you look at that picture of the ESP, you can see that Bluetooth antenna that was previously discussed. All right, so the speaker portion of the schematic here. So the speakers are more or less going to be connecting via jumpers to these portions that you see here on the bottom right side, the speaker array headers. They're going to be utilizing female headers onto there from the speaker wires that you see again on that same speaker that we covered before. We wanted it to be pretty modular, so in case there's an error with a speaker, maybe a broken wire somewhere, it could be pretty easily shifted out and you don't have to get a whole new PCB. The other thing as well, you can see the multiplexer on here. Again, it goes both directions, but in our case, we're going to be taking signal input in, and then we have 12 speaker outputs. As you can see, we have an enable switch there, power regulation, and then our binary selection inputs. All right, I believe this is the final slide on our PCB schematic breakdown. This is our additional peripherals on here. So one of the important parts of the design for the course is our push buttons to have an actual user be able to interface with our PCB and our system. In our case, we have 4 different buttons on here, 3 that are being actively used and 1 that is added into the design in case we want to add in a added function later on. Currently, it's just being used as a variable connection. The other 3 are going to be our start, pause, and end interrupts that would go to the ESP, then to the Jetson Nano in order to start the game, pause it in the case of the user getting to a point where we need to stop it in the middle of the game, and then also an end function if they would like to restart things. Obviously, these buttons would not be used by the blind user. This would be used by an assistant that would be helping and we would also have little tags on the side of the pool table to denote each of these buttons. In addition to this as well, we have our USB programming part of the connection to the PCB and to our overall system. You can see that on the right side here, it has a 4-pin jumper, as well as 2 diodes for protecting current flow within our connection to the USB ports there. All right, so this is the last slide for our user guidance system. This is our PCB prototype in a 3D model here. Looks very nice, kind of all the systems we've discussed here. It's going to be placed on the bottom of the table. Pretty slim dimensions. It should be pretty straightforward. I imagine that we will need to make a secondary and final version of this upon validation. Currently developing this board as we speak.
So in terms of budget financing, we are a self-funded team. We're trying to put in about $200 a person, so keep our total costs under $800. We're on track for budget. In terms of the major components, which was the pool table, Jetson Nano, camera, Bluetooth beacons, we've got everything and we're still well within budget. On the table here, we can see we're actually only taking up half of that cost. Once again, this is a 2-team project with the Scratch team, so we're only responsible for half of the pool table as we're all sharing that. In terms of the progress made, we're pretty well into our project. Our research is pretty much finalized. Our parts acquisition is mostly finalized. In terms of hardware, software design, we're pretty close to being at a point where we can start testing. We're finishing up integration right now. After that, we'll begin testing everything and making sure that everything is integrated properly. So our plan of immediate action is to finish up our individual subsystems and make sure the integration is correct. Once our PCB comes in, which should be coming up shortly, we want to validate that and make sure that it functions as it should. Once we have everything on our end, make sure it's integrating, it's working properly, the communication is fine, we will want to develop some tests. And then after that, we will go ahead and do the integration with the user team. We have tested out a Bluetooth connection between the 2 primary processors, and we were able to successfully transfer data. So it would mostly be the formatting of the communication between the teams. The actual means of communication has been established.